In this lesson, we're going to examine the other parts and pieces of compound interest and the things you can solve for. So for example, the rate, or how long you need an investment to be in for before you accumulate a certain amount. So we'll start with some examples, and basically it's just examples today. We got Giovanni. His banker told him if he invests 3,000 euros now, compounding yearly, it'll be worth 4,600 euros in 5 years' time. What's the rate of interest that his banker is guaranteeing him? So we'll set up our equation again from yesterday. So future value equals present value, 1 plus R over 100K to the N K, or Kn. We know he's got $3,000, or 3,000 euros. He wants it to accumulate to 4,600 euros. 1 plus, we don't know his rate, but we know he's going to compound this yearly. Another way of saying annually, once a year. And we're going to do that once a year for 5 years' time. So it's an equation we can solve. And we're going to solve this using some exponential rules that we know about. So first thing we're going to do, we're going to simplify, right, like we usually do for our calculators. So I'm going to write this as just R over 100, because 100 times 1 is 100, n to the power of 5. To make life a little bit easier for myself, I'm going to divide both sides by 3,000. Now 4,600 divided by 3,000 isn't a great number, so I'm going to leave it as a fraction for now. I can think of it as 4,600 over 3,000, or if I want to, 46 over 30, just counts out the zeros. Or I could even reduce that if I wanted to, divide both by 2 and get 23 over 15. I'm just going to write it as 46 over 30 for now. And on the right-hand side, I've got R over 100 to the power of 5. Well, I need to get rid of the exponent next, the 5. I can do that by taking the fifth root. So the fifth root of 46 over 30, and if I take the fifth root on the left side and do the same thing on the right side, I'm left with just 1 plus R over 100. Actually, I don't need this bracket anymore. Well, that makes my life easier. I want to solve for R. So the next thing I'm going to do is bring the 1 over. So just to keep it exact, I'm going to write this as 46 over 30. And then I want to bring that 1 over to become minus 1. And notice it's outside the root sign. Once I figure out that number, I'm going to multiply it all by 100. So I'm going to punch in my calculator fifth root of 46 over 30, put in brackets, bring the number over, the 1, and I end up with 0.08924. That's over 100. So to get R, I multiply by 100. I end up with 8.92%. R is actually a fairly easy thing to solve for, as it's the same process every time. The only thing that changes is your nth root, and the fifth root in this case. So I can give you guys one to try. Pause it and give yourself a try. 6 years after depositing $8,000 into an investment account, Irma receives a little bit more than that. She's got $12,000 now. During this period, the account returned R% compounded monthly. Can we figure out R? So what do we know? We know her future value was the 12,000. We know she started at 8,000. We don't know R, but we know it's compounded monthly, so times 12. And we know this happened 12 times a year for 6 years. So first off, we'll simplify again. Oops, 12,528 94 equals 8,000 and 1 plus R over 1,200 to the power of 72. And we're going to divide out the fraction. And again, this one isn't nice, so I'm just going to leave it as 12,528 over 8,000. I get R over 1,200 to the power of 72. Calculator is going to come in handy for sure this time because I need to take the 72nd root. All right, so 72nd. And if you need to in here, just use brackets in your calculator. 528.94 divided by 8,000. Okay. And we know we want to bring over that 1 afterwards, and we'll be left with R over 1,200. Okay, if we use our calculator and then do the subtracting 1, you should end up with 0.00625 equals R over 1,200. So multiply it by 1,200, cross multiply, right? And we end up with 7.50%. And we can solve for R. Not bad to do. Okay, next thing we want to be able to solve for sometimes. We've got Marina. She's saving to buy a boat worth $35,000. She has $28,000 in an account that pays 5.34% interest. How long must she wait? So I want to solve for n this time. So our equation's the same. One plus 5.34. We're going to do it twice a year. It's compounded half yearly. We're doing it 2 times a year for n years. So if I want to solve this, I have to solve for an unknown exponent. We know we can do that using some technology. So to do this, we're going to have to use our graphing calculators. We're going to have a line, and we're going to have an exponential curve. Okay. So we can find a point of intersection if we set our window appropriately. So take our graphing calculators, go to our y equals screen, we'll enter our line, 35,000, that's what I want to hit. My equation, my exponential growth is 28,000, bracket, 1 plus 5.34 divided by 200 to the power of 2x. And now notice I changed the 100 times 2 into 200, right? Just to make it easier for my calculator to work. Okay, I have to change the window. Now the window represents our years and our dollars. So our time starts at 0. I don't know how far into the future I need to go. For safety's sake, I'm going to put 20 years. I don't think it'll take me that long to make that much interest, but there's no harm in it. My window is my money. I need to start at 0, and I need to accumulate all the way up to $35,000. We like to go a little bit past that, so I'm going to put 40,000, just so I can make sure that it shows up in my graph. Remember our idea that we can't solve unless we can see with the graphing calculator. So I can definitely see the line, the curve. We'll go to our second calc menu. That's under trace. Second trace. We want to do number 5, intersect. We press enter, enter, enter. And we find that we can accumulate that much money in 4.23. Number n is in years. So 4.23 years. And this is all you need to show me, the equation that you're solving and the answer the graphing calculator gave you. Okay, it's something we've done before, we just haven't done it since we did exponential functions. We'll try another one. You guys try this one. How long will it take for $1,200 to double? It's invested at 5% compounded weekly. So our future value, and double this, is 2,400. We're starting at 1,200. We're doing 5% compounded weekly, so 52. But I don't know how long it's going for. So graphing calculator, we'll go clear out the equations we already had in there. So y equals clear and clear. The line we want to hit is 2,400. The equation we're working with is 1,200 bracket 1 plus 5 divided by 5,200 to the power of 52x. Gonna have to change our window. Okay. 0 to 20 years, again, that might be reasonable. We can always make it longer if we need to. I don't need to go to 40,000 anymore. I need to go to 2,400. So I'm going to just change this to 4,000. Graph, there's our line. Here comes our curve. Hopefully they cross. And they do on my screen. So I'm going to do my calc menu, second trace, number 5, enter, enter, enter. And we get an answer of 13.86 years. Or if we go to 3 sig figs, 13.9 years. Which is a reasonable amount, 13 years, for our interest to double, or our investment to double. Yeah. Some other things we have to worry about with money. Inflation. Inflation is something that affects us in the real world. Things that cost $1 10 years ago don't cost $1 anymore. Maybe they cost $1.50 now, or $2. Yeah, inflation's an example of compound interest. The way we measure compound interest in Canada, at least, is by using the Consumer Price Index. It's a special version of compound interest which has taken a basket of goods and see what the cost of them is, how the cost of them has changed over time. And the formula for this looks kind of familiar. Okay? Inflation equals C, that's your principal, your starting amount, bracket 1 plus R over 100 to the power of N. The reason there's no K in here is inflation is only calculated once a year. It's compounded annually. Now, you often hear in the media about our inflation other ways, so they're just breaking that rate up into different portions. So from June 2007 to June 2008, the Australian Bureau of Statistics recorded a CPI, Consumer Price Index, of 4.4%. If milk costs $2.07 in June 2007, how much did it cost in 2008 or 2010? So our inflation, our inflated value, if you will, takes our principal, 1 plus our rate was 4.4%. And in 2008, that's 1 year after 2007, exponent of 1. This would be 2007. Okay, nice and simple, put in a calculator, so we don't have to worry about the K this time. We end up with $2.16. If I want to do the same thing in 2010, oh sorry, this was 2008. 2010, I can do that. My same bag, sorry, was it milk? Yeah, my same bag of milk in 2010. Well, if the rate stayed the same, my exponent will now be a 3 because it's 3 years later, 2007 to 2010. That same bag of milk now costs $2.36, which doesn't seem like a huge change, but 29 cents is 20% of the value that milk has gone up, right? It's gone up a fair chunk. So inflation affects us all, and it's a good thing to know how it works. Another thing that goes along with that could be depreciation. When you buy things, the value of them often goes down. A good example of that would be a car. You buy a car, 5 years down the road, it's not worth what you paid for it anymore because it's depreciated in value. You couldn't sell it as if it was a new car anymore. So depreciation, again, is an example of compound interest. But in this case, the value is actually going down. So if we're talking about depreciation, we take our initial value, our principal, and this time it would be going down R over 100 to the N. Okay. Again, exponential decay, if you will. So if we look at this last example here, we got VJ. He paid $30,000 for a car. Value depreciates at 9% per year. What's the value of the car after 6 years? So his value started at 30,000. It's going to go down 9% per year. That's going to do that for 6 years. And just before we answer, I want you to stop and think for a second. Doesn't this look suspiciously like our standard exponential equation where we have an initial value and a rate of change? I think that kind of looks basically the same idea, right? That's all finance really is examples of exponential functions, and growth and decay. If you use our calculator, we should get $17,036.08. Okay, so that price is cut almost in half from the day he bought it to what it's worth 6 years later. That's pretty accurate with cars. They actually use percentages at much higher rates than 9. That's the end of that lesson. The homework is a handout today, so try the examples. You have to be able to solve for R, solve for N, and know some small stuff about inflation and depreciation.